right, maybe we can get started. Good afternoon, everybody. We're very happy to have our very own Wim van Rees tonight to talk about his exciting work. So, Wim did his undergraduate and master's degree at Delft in the naval architecture department. So you can doing this, just telling me work on computation of the experiment too. So you're going to hear some other aspects of his work. Right? And then he went on to get a PhD degree at ETH in Zurich with Petros Koumoutsakos on computational engineering. He did some very nice applications to fish swimming, some very original work with implications on the dynamics of swimming. So that's how I got to find out early on, as early as 2011, I think was the first time I saw Wim's work. And they had some very interesting aspects on the involvement of the added mass in fish to produce thrust, some really nice results. So he continued as researcher at ETH, and then he moved on to Harvard University with exclusion for that, Mahadeva. He did a lot of work on what Mahadeva calls the morphogenesis of plates and shells, which means morphing and expanding and doing other things with plates. It's a very intriguing concept. Some very nice work on it too. And then he came to MechE in 2017, and ever since he's been working on some very nice topics in fluid mechanics. So now we're looking forward to listen to his work on vortical waves toward morphing fins.
Thanks so much, Michael. All right. Put that away. Cool. All right, thank you everyone for coming. Rainy Friday afternoon. So I'm going to talk about some of the work I've been doing over the last, I guess, 5-6 years. And the subtitle here, leveraging high-fidelity simulation techniques for ocean engineering challenges. I'll start a little bit around that because that kind of sets the theme of the work that we're doing in our group. So if I take a step back, so very high-level challenges in ocean science and engineering that inspire some of the work that we do, we can enumerate many applications, right? We can think about coral bleaching, emission reductions. This is a ship with a little kite that's pulling it. Agile underwater vehicle fleets inspired by fish and fish behavior. Just plain exploration of all the organisms that we haven't found yet in nature. There's a lot of applications in ocean engineering, but I want to kind of take out 3 specifically, just to dive a little bit deeper into what are the challenges that we have to kind of face to solve such challenges. And those are microplastic transport, offshore aquaculture, and offshore wind. So microplastic transport, we're familiar with, that being a problem in our environment. Offshore aquaculture is a way that we can, sustainably supply food to the population in a way that scales better than almost any other solution that we can think of at the moment. And offshore wind is, the new direction for renewable energy harvesting. So these are very kind of, big topic areas. But then if I dive a little bit deeper into the fluid dynamics, the specific problems, right, underlying some of these things, starting with microplastic transport, a very recent review earlier this year about the fluid dynamics challenges in predicting plastic pollution transport in the ocean lists some very specific problems that we have with current models, right? And this is, Themis knows this well. But the transport of 3D particles in a flow environment, there's theory for that. There are models for that, and they're well validated and well used. But microplastics are a little bit different because they're non-rigid, they're oddly shaped, they're inhomogeneous, and they're often covered with a biofilm, a viscous layer that affects their transport. And so, existing modeling techniques and simplifications might not hold for describing the transport of 3D particles. So now we go from a very big problem to something very specific, a fluid dynamic problems that we have to tackle. And we can do that also for offshore aquaculture. If we think about the forces on a submerged net, which ultimately drives the motion of an aquaculture structure, this is, flow through a porous screen, right? A net is like a porous screen, and the flow goes through and exerts a certain drag on that net. And there's, a lot of recent interest from all sorts of different directions into forces on submerged nets. But one thing that's common in these studies is that there is very little information on data for free three-dimensional flow, specifically looking at the pressure and the velocity distribution across a net, right? And this is another very recent kind of overview paper on flow around and through a porous screen. So we go from, again, a big application to a very specific scientific problem that involves fluid dynamics and fluid structure interaction. And then we can repeat that for offshore wind as well. Here we have wind-wave boundary layer coupling, which is crucial in predicting the marine atmospheric boundary layer behavior. And this is, again, a very small-scale problem. It is multifaceted, but one part of it is the onset of how wind drives waves, how waves break, how wind separates over the waves, and then affects both, the growth of the wave, and the growth of the wave feeds back into how the boundary layer of the wind looks like. So again, very specific scientific challenge that is just kind of out of reach of what we can simulate at the moment. So these are just three examples that to dive a little bit deeper into these challenges, but there are some common features here. They're governed by 3D inertial flows. They are governed by flow structure interaction or other multi-physics problems, right? So here the viscous layer, here the fluid structure interaction, and here the multi-phase flow, right? And they push the limits of routine numerical simulations, of routine high-fidelity numerical simulations. So I'm not thinking about high-fidelity simulation flow past a ship, like on that scale. I'm thinking about very specific scientific challenges that are just kind of beyond what we can do at the moment. And those types of application inspires us to do work, both on the numerical development and on applications. So when I talk about leveraging high-fidelity simulation techniques for ocean engineering challenges, I talk about these two aspects. And so on the methodology side, what we do in the lab is a lot of numerics, and I'll talk a little bit about some of our contributions in the second half of this talk. We try to couple those numerical methods with optimization and reinforcement learning, so using data-driven methods to solve inverse problem or control problems. And I'll talk about an example where we use a data-driven surrogate model to do some of that. And then on the application side, we try to span all sorts of different applications, starting from pure flow physics, which is the first topic I'll talk about, to flow structure interaction, where we have both a flow and a body interacting with that flow, all the way to pure solid mechanics, right, morphing structures. So here we span from fluid dynamics to solid mechanics, and of course the big topic is combining that in between. So it's some high-level kind of perspective of where we are working on and what type of problems we're trying to tackle. And so now I go into what I want to talk about today, which is a little overview of my presentation. I want to talk about two applications. One is the dynamics of trailing vortices, and that's been done by Limbo, who's right there. I want to talk about some of the hydrodynamics of morphing fins. This is done by my former postdoc, David Fernandez-Gutierrez, and my current postdoc, Hamid, who's right there. And then I want to end with our work on numerical methods to kind of push what's possible in multi-physics simulations, which is done by my former postdoc, Thomas, and my current grad students, James and Shinjay. Awesome. Nice cluster. OK. So let's start with dynamics of trailing vortices. So how do we use numerical simulations here to gain some insight into the fundamental physical features of these flows? So trailing vortices are common in many applications, not only ocean engineering. The main kind of research is motivated, in fact, by aircraft and rotorcraft tip vortices. But they're also prevalent in submarine sails, in nature, birdwing tip vortices. And this is from my master's work on ship cavitation. This is a picture of a model propeller that has a cavitating tip vortex, right? So another kind of thin vertical structure, elongated vertical structure behind an immersed boundary, an immersed body. And so the dynamics of these trailing vortices, they determine many quantities, but some important ones are the performance and stability of trailing bodies. So if I have an airplane behind this airplane, or if I have a rotor behind the current rotor, right, in rotorcraft. Wake signature and detection, right, it's specific to submarines maybe. And ambient mixing on a large scale, right, how these vortices persist and they contribute to ambient mixing in the atmosphere. And so for that reason, there's been a lot of interest in dynamics of trailing vortices. It's a very old kind of field in vortex dynamics. Most of the traditional research has focused on the stability of vortices to centerline perturbations and ambient strain fields. So what if I take a vortex like that and I perturb the centerline a little bit? How does that affect the stability? But we've gotten interested in what happens when we change the core size of a vortex. So let's say I have a straight centerline and I just undulate the core a little bit. What happens then? And so there's been some work in that direction, low Reynolds number simulations. So these are order of 100 in circulation-based Reynolds number. And there's been linear stability analysis for very small perturbations. But nothing pushing the boundary here in terms of large perturbations and high Reynolds number. And at the same time, the motivation for studying this is because there have been some experimental observations of what potentially happens when this occurs. And this is a single picture from a one-paragraph excerpt of an annual review of fluid mechanics in 1998 by Spallard, who worked for Boeing. And he showed this kind of sketch of an experimental observation, some sort of pancaking on this trailing vortex. Right? And there's been one isolated one-off paper in 2005 that showed that using a numerical simulation, but never really got into what is going on in the vortex dynamics of this instability. And so we were interested in what is the vortex dynamics of this bursting, right? This pancaking, and how stable is it? If I do that on a straight vortex tube, or if I see it on a curved vortex tube, how does it affect the stability and the dynamics? And the effect of bursting on the evolution of helicity, which I won't get into today. So Lingbo set up some simulations. So we create a vortex tube with a little bump, right? This is a core size expansion. The whole vortex tube is 3D but axisymmetric. We have a region of sinusoidal perturbations. So this is like a kind of a sine wave here. So there's this perturbation of length lambda and then a straight section of length L minus lambda. And we define the perturbation amplitude as the ratio between the maximum amplitude, the maximum core size, and the minimum core size. Right? So this is the sigma of the Gaussian that determines the core profile. The Reynolds number of our simulations is 5,000. And we have boundary conditions that are periodic in the z direction. So we look at a section of this tube. So the bursting will happen here. Small spoiler. And the computational domain, we choose it like this. So we have one period of the vortex in our domain. On the numerical method, this is a method that I've been using for a decade now. A remeshed vortex method is well validated. These simulations are typically about 10 to the 8 grid points. And we use a cluster. We have about 400 cores that we use for these simulations. And this takes a couple days to run a single simulation here. So if we do that and we let the simulation go, we see what happens. This is the center part of the vortex tube, the kind of the squeezed part, the thin part. And then at these edges, you kind of see it funneling out, right? So you see the core size increase. And this is the vorticity magnitude. And so if I run my simulation, I get this pancaking, right? Just like in the sketch of Spallard. And then if we look at this a bit more carefully, we see we can visualize something else than the vorticity magnitude, which is kind of the field lines of the vorticity field, which are the vortex lines. So here I look at the vortex lines. You can again see the kind of the expansion. We plot vortex lines on this rake going around this circumference. And we color them by the azimuth of vorticity, which is the component that is rotating around the center line, which is 0 in the beginning because all these vortex lines are parallel to the center line. But as we let the simulation go, we see these twist waves appear. So the blue and the red are opposite sign twist, and they come together and collide, leading to bursting. So if I play this again, you can see them here, and then bursting occurs with this pancake. So this is what we started from, and we wanted to analyze a little bit what's going on here physically, right? What are the mechanics of this vortex, of this bursting? And so we divided the flow into these phases. The first phase is what we call the early phase, which is the starting from that initial condition, getting to the twist waves, right? But before they start to collide. And so the mechanism here is something that's been known, but it's useful to review it. So when we have a vortex with a larger core here than here, these differential core sizes are associated with differential rotational velocity. So the rotational velocity is faster here than here. And so if I think about what happens to a vortex line, it will get tilted out of plane, right? Because it gets rotated faster in the interior part than in the exterior part. So these vortex lines are getting twisted up on the left side and with an opposite sign on the right side. And so we get these twist waves, which are these component that's circumferential to the center line. And they propagate, they move, and they are visible in the simulation, right? These are these twist waves. You can see them the vortex line twist around the center line. And we did some analysis of what happens to, how does the speed of these twist waves change as a function of time and also as a function of the core size amplitude. And so you can see here, this is as a function of the location along the center line. The twist density at the center line is increasing with time. So you get this peak right until it hits the center plane, this middle plane. And that's when bursting occurs. And the bursting itself is when these twist waves come together. So here we have a snapshot just before they meet. And then as they meet, you get this expansion of the center structure, which is governed by kind of two vortex rings. You see them here, the red and the blue one. These are two vortex rings that are scrolling and radially expanding. And so we have a growth phase where these twist waves come together and grow the ring. And then we have a relaxation phase. So after some time, we have a kind of a maximum diameter or maximum radius, and we slowly relax. And you see the twist wave reverses, right? What was going one-handed here is now opposite-handed down here. So we get twist waves going out of the bursting plane. And so this is interesting. No one has ever really looked at the vorticity distribution in a bursting phenomenon like this, right? Besides those sketches of the pancaking. And so if we analyze a little bit more what's going on inside this early phase, the bursting, we can think about what causes the growth of these ring pairs. Here's again some vortex lines that show right during that phase what happens. You can think of these vortex lines as being kind of starting out as straight lines, and then getting these hairpins that turn around the center line. Right? And if we look at the vorticity distribution in the center plane, which is axisymmetric and also has very nice symmetry properties, we just see that the vorticity that governs these rings is being pushed outwards. There's a radial transport, UR, and they're also being compressed or stretched. So at the center, it's being compressed, and at the outside it's being stretched. And so you get this radial expansion, just as if two vortex rings would meet head on, right? But these are not rings because these structures are connected to the tubes. And then the question is, what arrests the growth of the ring pairs? Why doesn't it just keep going? Well, one conceptual way to see that is that prior to bursting, we had this picture where the twist waves move towards each other because the bump was on the outside. And now as we burst, we essentially have the opposite, right? So we have this larger radial diameter in the core size here, and so the twist waves will reverse and move away from there. So very, in a nutshell, why this bursting reverses, and you can think about the equation for the azimuthal vorticity having a term that changes sign as the vortex lines expand radially. And so because the twist waves move away from the center, they kind of move back to the periodic edges, and you get another bursting event there, right? And we saw that in the initial movement. Bursting keeps going, sloshing in this kind of periodic domain. And how does that affect the large-scale picture of the flow? Here's the evolution of the energy as a function of time. And we have different lines. They are characterized by different initial core size amplitude. So essentially measuring the strength of these twist waves and the strength of the bursting phenomenon. And in all cases, we have a dashed line that we compare with, which is just a kind of a vortex that's just undergoing viscous decay as a reference. And so we have a significant loss of energy due to these successive bursting regimes, right? The vorticity keeps increasing, entropy keeps increasing, this dissipates energy. And so these kind of perturbations, they kill the vortex faster, right? You lose energy because of that. And we can quantify the amount of energy being lost here. So that's the straight line case. We have a straight center line, and the vorticity structure remains axisymmetric pretty much the whole time. And so we recently started looking into more realistic center lines. What if they are curved, right? And so this is the straight line case again, looking from the side with the bursting, and then the second bursting, and then the third bursting. And then if we start to curve the center line into kind of a helical shape, this bursting is way more susceptible to instabilities, right? Because the curvature of the center line and the constant motion of this center line causes the bursting to experience a shear deformation that immediately becomes unstable at this Reynolds number and destroys the kind of the coherent structure of this vortex at late time. And so if you do bursting on a vortex ring, you can see the same thing, right? This vortex ring immediately becomes, kind of disintegrates into a lot of small-scale structures around this center line. All right, so the key features of bursting coming out of these simulations are bursting is self-arresting. So the expansion of the bursting structure leads to opposite-signed azimuthal vorticity, right? So this is a key difference from just vortex ring collision. As these things come together, it automatically means they have to, at some point, decay, right? This is a self-arresting process. But it's associated with strong entropy production, right? And thus accelerated energy dissipation. And there's a strong potential to destabilize the core structure, right? And then further increase the energy dissipation, which is especially pronounced when either the twist differential is large, when we have a large core size perturbation, or when the center line is curved. And it's even more susceptible to this destabilization. So we've been working on this for a little bit, and I'm excited about some future directions that we're trying to get into. One is to think about the inverse problem. So can we optimize the perturbations given a late-time flow metric? Can I find the perturbations I need to put in the beginning so that my energy is maximally dissipated after some time? And then another one is the prediction and simulation of the generation of these core size variations off of a boundary layer, right? Can I put an actual boundary in the flow, which is the source of all vorticity in incompressible 3D flow? So can I put a boundary layer and modulate it in a way that I can induce this bursting in practice? And one thing that's interesting there is that I found a sketch in a textbook from 1908 that quotes, the filaments will evidently wind around another like the strands of a rope. And this is a sketch of a wing and a tip vortex coming around. And I find it very cool to compare these two. I think about a sketch and a multi-core numerical simulation showing these features qualitatively and then more quantitatively. OK, so this last topic is I'm going to take that into my work on numerics, right? That's some of the motivation for improving on numerics, because this is not possible with current numerical techniques when we modulate this boundary. All right, so I want to switch gears and move to this other application, which is the hydrodynamics of morphing fins. Here it's David's and Amit's work. And so here we are using, again, numerical simulations to tackle a different problem. And if I take a step back and look at the motivation for what we're doing, we know about soft, deformable, actuatable structures in nature, right? We know that fish can change the curvature of their fins and actively control that, as well as just being deformed due to hydrodynamic forces. And we also know that more and more we see soft, deformable, actuated structures in engineering from Harvard, from MIT, from other groups around the world. Different strategies to kind of morph and change the shape of a fin, passively, actively, all sorts of different mechanisms. But there's some fundamental open questions in this, putting this together. And I'm going to list some from solids to fluids, right? So in the solid domain, the inverse design of shape-shifting structures on their own, even without hydrodynamic forces, is not there's not a clear systematic procedure for that. Everyone has their own unit cell and does their own kind of ad hoc inverse design for the shape-shifting part. In the fluid domain, often when we start to think about deforming fins, we don't know what the gains are that we can expect. What are the hydrodynamic optimal shapes that the structure should have so that we can find maximum performance benefits, even disregarding the structural deformation that achieves that specific shape. And then the fluid structure interaction problem is how do we combine all that together, right? How would we design the structure so that when we put it in the flow and the forces act on the structure, it deforms into a shape that is beneficial for our ultimate application. And so I don't want to put anyone down, but this is a video from UCSD in 2018 where they focused a lot on the material side. So this is a dielectric elastomer swimmer that is being actuated and swims. And this is from a group that does a lot of the structural design. And my thought is, let's say I have that capability, how would I create the best possible design I can make, right? And not try to put it in a way that a fish swims, for instance. So I want to talk about those three topics, right? So solid, fluids, and FSI. So starting with the solid, one avenue for morphing, for creating a morphing structure, is 4D printing. This is a concept that's been coined by Skylar Tibbets here at MIT in 2014. And this is a very popular paper that was coming out of my group in Harvard, where they 4D printed a structure. So 4D printing is you 3D print a structure that has some sort of response to an ambient stimulus, in this case, water or a solvent. And as a response to being embedded or exposed to the stimulus, it will change its shape. Right? And so there's a very nice set of problems. And the underlying mechanism here is differential or inhomogeneous growth. Right? So you have a structure that responds inhomogeneously or differentially to a stimulus. And that changes the elastic energy. And so your equilibrium embedding changes. And this is governed by a theory of non-Euclidean plastic plates more broadly than just kind of 4D printed structure. So a couple of questions. Can we predict the equilibrium shape after applying a given growth pattern? Can we design the growth pattern to find a certain target shape? And can we realize all this in an experimental system? Those are kind of the questions I tackled into my postdoc and then coming into here for the first couple of years. And so in a one-slide set of my contributions on this topic, the prediction, we solved it using numerics. It's kind of my go-to here. So we created an open source code for simulating shape transformation of elastic sheets with differential inhomogeneous growth. And we validated it with some of these experiments from the group in Harvard. So we kind of managed to reproduce their shape transformations that they saw experimentally using only numerical simulations. On the inverse problem, we derived a theoretical solution for the inverse design of growth pattern of a shape-shifting elastic bilayer. So we basically came up with a very simple theory that says if you want to achieve this target shape after growing, this is how you should pattern your initial bilayer sheet. And then using simulations, we could demonstrate that this works by growing a circular sheet into the shape of an elastic, of a human face. And then I worked with a collaborator at Harvard and then Boston University to generate a structural lattice design that can achieve unprecedented complex and predictable shape changes in 4D printed sheets. So this is all experiments by Will Bowley, who is now at BU. And we came up with this lattice structure that was 4D printed. And after you apply, in this case, a temperature change, it will change its shape into a 3D sheet. And then we thought, let's tackle the phase problem. So I took Gauss, a painting of Gauss, and I created a 3D model out of that using one of these AI kind of magic tools. And we inverse designed that phase, and then we printed it, and we showed that after applying the temperature change, we do achieve, from a flat sheet, a complex 3D shape like that. And that got us some nice attention, and they attributed it all to me, which is not exactly what is fair, but that's what it is. So on the 4D printing side, right, we have all this capability to create morphing structures. What performance benefits can we expect if we bring that into a flow environment, right? So now I go back to the flow problem and think about what if I could have infinite curvature control on my shape, what performance benefits would that bring? And so we did some work with my postdoc David, inspired partially also by the fact that the fins of ray-finned fish deform passively and actively. So this is a picture, a movie from George Lauder's group where they film the tail of a fish is deforming. And there's some more theoretical work and from biology into the mechanisms underlying the active control of fish to change their fin shape. And so we set up a bunch of simulations, 2D and 3D, where we impose the curvature variations on a flapping foil. Right? And so we chose Reynolds number 1500, fixed the Strual number, chose a harmonic motion with the pitch being out of phase with the heave. So in 3D, that looks something like this when the fin is not deforming. So this is our reference case. And then we see what happens if we start to deform this fin as it's flapping. Right? And the key results, the headline results, is that if we change the camber in phase with the pitch, we get the maximum thrust. And we can quantify that. We get about 70% increase in thrust and 15% increase in efficiency at the same time over a rigid foil. So time is from right to left, and this fin is kind of plunging down. This is the downstroke. And the maximum curvature occurs right when it's kind of halfway through the stroke. And so putting a maximum camber at that point in the cycle is maximally beneficial for generating thrust. For efficiency, it's slightly different. You want the camber to be more in phase with the heave. And so maximum curvature happens roughly at the beginning of the stroke and the end of the stroke. And that leads to a 35% increase in efficiency over a rigid foil. And we also looked at what happens when you do span-wise curvature. So this is a fin that is deforming span-wise. So out of plane, the top rays are following a different phase than the middle rays. And that's really not that important in the whole picture. So chord-wise curvature is the dominant effect. And we can quantify what happens for the span-wise curvature, but it's not in the big picture that important. And so just to kind of emphasize the abilities that you can get when you do curvature variations on a flapping foil, I look at 3 cases. One is the rigid foil. This is the thrust coefficient during the downstroke. And the rigid foil is in black. And then the maximally efficient foil is in green. And I chose another foil which is equal power as the maximum efficient one, but much smaller thrust. And if I look at 5 times during this cycle, here time goes from left to right, I can find that the minimum efficiency foil has this curvature kind of in the opposite sense as you would expect. The rigid one stays rigid, and the maximally efficient foil has this curvature kind of in phase with the heave. And so the range of efficiencies that you achieve by just modulating the curvature, right? These are the same leading and trailing edge kinematics as the rigid foil. Just changing the camber over time is very, very, very large. And so this mechanism of changing curvature over time in a stroke allows you to respond, right? So you can do maximum thrust for one part of the operational profile and then switch to maximum efficiency if you want at a later point. So I find this very interesting to be able to quantify the gains that you could get if you are doing your fluid structure design perfectly, right? This is kind of the upper bound in terms of performance benefits. And then putting it all together is an inverse design problem. So if you want to combine the capabilities of morphing fins from a structural design with a flow environment, you have to think about how to optimize the structural design of a morphing foil. And specifically, I'm interested in a high-dimensional structural parameter space where, like 4D printing, I can change the response at every point on my structure, right? So I have a lot of degrees of freedom in my structural design space. How do I solve that inverse problem? And so we started thinking about a conceptual approach to doing that. And if I think about the standard FSI design loop, I have my flow solver and my structural solver. The structural solver gives the shape to the flow, and the flow gives the loading to the structure, right? That's kind of the coupling. And the flow solver is parameterized by the flow conditions. The structural solver is parameterized by the design. And out of this FSI design loop comes the aerodynamic performance of this foil. And so our plan was to think, what if we put a surrogate model to find the relationship between the shape of a structure and the aerodynamic loading? If we can train a surrogate model to predict that, I can, and that's a rigid foil problem. I don't need to deform the foil to do that. If I can train a surrogate model to do that, I can evaluate or optimize any structural design using only the structural model, right? So I can go very high in my structural parameter space because I am calling a surrogate model to do the FSI coupling. And so we developed a proof of concept with Hamid, my postdoc. We thought about a simple structural design, which is a NACA linked airfoil. And so here we have an airfoil with a set of links connected by hinges, and the hinge angles are fully determining the shape. And the aerodynamic loading that's relevant to solve the structural problem is the aerodynamic moments on each of these hinges. And so we trained a surrogate model to find this relationship. Our underlying solver was X-foil, so we were able to swap out the surrogate model with the exact solver. And then we parameterized the structural design by the stiffnesses of the hinge springs and the rest angles of the hinge springs. And we did a case study for a 4-segment airfoil. The objective here was to optimize the torsion spring stiffnesses and the torsion spring rest angles to achieve approximately constant lift and minimize drag across 4 different incident angles. So a big design problem to basically say if I can design an airfoil that actively deforms through the aerodynamic loading to keep the lift roughly constant across a different set of inflow angles. We trained the surrogate model using 400 samples of training data, and we called the model 42,000 times to evaluate, to solve the optimization problem. So that's a massive gain that otherwise we would have to call xfoil 42,000 times. And the results are pretty good. The optimized structure is this red line, and the rigid structure is the blue line. And the black line is what we would get if we set the spring stiffnesses to infinity. So we just do a design optimization, a shape optimization, and not an FSI problem. The drag is much lower. The lift here is roughly, the red line is more flat than the blue line, right? So the lift remains more constant for that optimized structure. And the shape changes quite a bit. So here is what happens at 0 degrees. Here's what happens at 9 degrees. And the deforming shape is shown in red, right? So the red shape is deforming as this structure is loaded, whereas the black shape is the undeformed FSI shape. So this approach allows you to arbitrarily increase the design space for the structural side. We can put nonlinear springs without additional cost, right? We just call the surrogate model more times. And the surrogate model gains will be even more pronounced when we switch xfoil for a solver that is Navier-Stokes, right? That's more accurate and more high fidelity, which is ultimately where we want to go with this. So to summarize that, I think we have a lot of technological opportunities in additive manufacturing and 4D printing. We have inspiration and guidance from biological systems, how to use those materials. And we have numerics that can give us a framework for prediction, optimization, and control, and putting this all together. In terms of future work, one thing I'm very interested in is to again, look at multi-physics simulations of smart morphing structures, and also focusing on high throughput as simulation pipelines. So when we train data-driven models, we need to churn out data. We need to generate a lot of results. And so high throughput becomes a relevant metric to judge your simulation technique by. All right. So we talked a little bit about these two applications. And so I want to switch gears for the last time and talk about numerical methods for multi-physics simulations. So besides the examples I gave at the beginning, these two applications both also have their motivation to think about improving numerical methods, right? We want to simulate vortices coming off of boundaries, and we want to be able to simulate kind of FSI actuated structures in a fluid flow environment. And so why do current methods not suffice for that, right? So this is what I said. Many applications are just outside of the reach of current solvers. And specifically, if I try to emphasize what is the problem, I think a lot of applications can do high Reynolds number and 3D, or high Reynolds number and maybe multiphysics in 2D, or 3D multiphysics at low Reynolds number. But a lot of these applications I mentioned sit right in the middle, right? You need all three of these components. And why is it hard to go there? We need to distinguish between the solution methodologies that are in play right now. So I need to go to the numerics and talk about how to solve PDEs on complex domains, which are these multiphysics problems. And so the traditional approach to do any simulation, any CFD, is to create a mesh, a body-fitted mesh that conforms to the body boundary. And in a very simple sketch, that kind of looks like this, right? So this body is a body-conforming mesh, this triangle mesh. And as the body is moving, right, like think of this as an FSI problem, this mesh is deforming along the way. And so these type of methods get you very accurate near-wall solutions. They are relatively easily extended to high order, but the mesh generation and adaptation is expensive and possibly complex, right? Hard to achieve. And so this other class of methods, which are called immersed methods, are emerging, and they superimpose an interface on a background structured grid. So now we don't change our grid, and the body is kind of doing what it wants through this unchanged Cartesian grid. So no meshing is required, and the structured grid allows for fast PDE discretization. And within this class of methods, we need to go one level deeper and think about the sub-methods in there. The majority of techniques are using continuous forcing, which is essentially mollifying the interface. So your interface is a region of smooth region that goes from, let's say, flow to solid over a few grid points, right? And so you don't have a sense of, this is the end of my solid, this is the start of the fluid. But it's very simple to implement this because you can just add a forcing term on these grid points that are covered by the interface. So easy to implement, but very difficult to make accurate, to extend to high order. On the other side, there's discrete forcing methods, which enforce a sharp interface where you're really keeping track of where your body intersects the grid. And those methods can theoretically extend to higher order, but are complex to implement, especially when you involve 3D and non-convex bodies and things like that. And our method of choice, which is the immersed interface method, sits in this corner. Right? So we're trying to address this problem of how to implement an immersed interface method that can extend to high order. So what is an immersed interface method? Let me do this is a 208.6. Before I get there, the strategy that we use for high-fidelity multi-physics simulations is the way we tackle this problem. We call it Murphy, which is multi-resolution multi-physics. And we rely on 3 techniques. One is this immersed interface method that I'll talk a bit more about. And then the other 2 components, which I won't get to today, are using block-structured octree grid structures and wavelet-based dynamic mesh adaptation, which allows us to change the grid dynamically to the solution. And so the way immersed interface method gets us high order. It gets us flexibility in applying boundary conditions. And this is suitable for coupling different physics. The block tree is kind of the computer sciencey part of this thing. How do we create a solver, a software that can use current supercomputers and large-scale computational resources? And then the wavelet-based mesh adaptation is a very interesting numerical problem. I'm happy to follow up on that, but I won't be able to get to that. This is how to change your grid dynamically to the solution. So the immersed interface method, now we get into the 208.6. If I apply a finite difference scheme on a regular grid, and I don't have a boundary, and I want to know a 1D first derivative at this point x1, I just do this. And we taught this last week in 208.6. If I have a boundary that's not immersed, I change that left grid point with the wall boundary condition. Right? And now if I have an immersed boundary, I don't have the ability to just replace my grid point. So roughly what we do at the very first order is to construct a polynomial function that interpolates through our grid points and the wall boundary condition, and then evaluate that polynomial at the point that I'm missing in my finite difference scheme. Right? And so it's essentially some sort of one-sided finite difference scheme that uses information from the inside of the domain to to fill in a ghost point where we don't have information. In a bit more detail, this is a very large history in IAM. Our approach reinterprets earlier formulations. This kind of polynomial extrapolation approach is something that we derive to reinterpret existing formulations. In higher dimensions, it's not that straightforward. You cannot do easily 1D interpolants when you have convex shapes because you are missing points that are inside the body. And so we use weighted least squares to construct multivariate polynomials for that. We don't have a lot of the small cell problems that maybe cut cell finite volume methods have. We can generalize. I showed for a Dirichlet boundary condition, we can generalize to arbitrary boundary conditions. We can discretize various partial differential equations, and we can do what we call multiphysics, where we have 2 different domains connected through boundary conditions on an embedded interface, like jump boundary conditions, continuity of the function or the flux or things like that. So we implemented that in a 2D Navier-Stokes solver. We use a vorticity velocity formulation, which enables us to keep our domains very compact while still simulating external flows. Previous work on these methods have all been limited to stationary boundaries and single bodies, so we extended to multiple bodies and moving boundaries. And the equations that we're solving are essentially a vorticity transport equation and then a Poisson equation for the stream function. And our method has been, at this point, we've kind of matured it, so we can do all sorts of cool flow simulations. This is a flow past the MIT logo that is embedded on a regular grid. So just as an example, it's not the best example of an arbitrary shape because it's very rectangular, but it is embedded on a Cartesian grid. Periodic domain, so this is a cylinder where you can think of this as an infinite array of cylinders, so the wake of one cylinder hits the other cylinder, and so forth. And we are working on internal flows where we're comparing in a workshop to body-fitted grid methods and seeing how accurate are we with our immersed approach. and two-way body coupling, where we have in this case, is a cylinder falling under its own weight in a flow. And so those are like some of the test cases we've been working on. We're applying it now to some applications in ocean engineering. This is a hydrodynamic interaction between overtaking bodies, where this kind of ellipse is overtaking the other ellipse, and we're looking at specifically what lateral forces are experienced by these bodies during this operation. And we're interested in this aquaculture net, so we're simulating the long-time flow here past a porous structure. So these are 6 cylinders embedded in a flow, and part of the flow will go around, part of it will go through, and there's a very nice transition when you increase the cylinder count to having the flow kind of choosing to go around versus going through, so the wake characteristics change quite a bit. And so from here, we can get a first sense of the distribution of velocity and pressure on a porous structure. And this simulation is I think it's about 500 non-dimensional time, so we can do very long time sequences here. Just to highlight the benefits of high order, right? So we compare to a first order penalization method, which is what I've been using in my research so far. And we choose a test case here where there's a pitching plate with 2% thickness, Reynolds number 1,000, and the flow kind of looks like that. So this plate is starting out and then pitching down, and there's a big leading edge vortex coming off the tip, and so of the leading edge. And we simulated this with both our new method and the old method. This is a convergence plot, which is doing what I told you our method does. The old method converges at first order, the new method converges at second order. But what this means is that for a specific error that we need, for instance, 10 to the minus 4 in the L2 norm, we need about 20 times fewer points in 2D, right? So we get a substantial gain, and our cost is not 20 times larger, it's maybe 2 or 3. So we get a substantial gain just from switching to a high order method, right? So this is encouraging for the research that we're doing in 3D. And if we are more specific about the error that we make, this is the vorticity field coming out of our first order method at a fixed resolution, 256 here, in red, and then the second order in blue. These are contours. And looking at the close-up here at the leading edge, there's a lot of differences in the detailed structure of the vorticity field. The red penalization, the red first order method is missing a lot of the fine-tuned features. And I think going to multiphysics and fluid structure interaction, this is what becomes very important, right? This drives the stresses on the structure and the solid mechanic behavior. So the benefits of high order are not just kind of in a convergence plot. I think they're very physical in the results that we're getting and the price we pay for them. So I want to end with some of the extensions of this method. So this has been all 2D Navier-Stokes. In a bullet form, this is all James. He's done a GKS stability analysis for 1D hyperbolic PDEs with embedded boundaries. So how stable is this? And that's not been done for this immersed interface method yet. So we can have formal proofs of stability. We've done a substantial error analysis of the high order time integration for problems with moving sharp boundaries. So if I have a body that's moving across a Cartesian grid, how does the error behave, and can we make that high order? And we have implemented this all in our in-house Murphy kind of 3D adaptive grid framework. Some consequences of that are that we can do all sorts of problems. So here we can solve linear elasticity inside an analysis on a uniform Cartesian grid to fourth order accuracy. So we can branch easily to elastic problems. And we're thinking about coupling these with like level set based topology optimization, where you don't have to worry about meshing your grid every time you evaluate a new iteration. This is just a kind of general capability, 3D advection diffusion with a moving boundary. It's a bit of a test problem, but this is a sphere that's moving through a domain. There's a scalar embedded, and we're solving the advection diffusion on the scalar. We get very smooth fields on the boundary, so this is also important for FSI. We can evaluate quantities on the embedded surface. And this is third order accurate in the infinity norm. Very smooth surface quantities, high order temporal error. And then we can play around again. So if we think about advection diffusion with a boundary source, so like a heat problem where the boundary of the body is at a constant temperature and the flow is kind of moving past. This is the MIT logo with a constant Dirichlet boundary condition and a flow moving top to bottom. And the heat is, the temperature is being transported down while it diffuses inside the flow regime. And now we can make that multiphysics by not only applying not just applying a boundary condition on the surface, but do a conjugate heat transfer, where inside the body there's diffusing heat, there's a heat source inside the body as well, and the boundary conditions are continuity of temperature and continuity of the heat flux, right? With a discontinuous diffusivity inside and outside. And so that looks something like this. This is our contribution to Halloween here, the color map. But you can see how the features of this problem are very clear. This little dot here is losing a lot of heat by being very exposed, whereas down here not as much, right? And so these are third order, fourth advection, fourth order diffusion, fourth order potential flow, and I don't think anyone can do this type of problem at high order with an embedded method at this point. And this is kind of ready to go into 3D. All right. So I'll skip this. This is on the wavelet grid adaptation. And conclude with some perspective. So I said leveraging high-fidelity simulation techniques for ocean engineering challenges. I hope I've convinced you that current ocean engineering challenges are governed by complex geometries, moving boundaries, and multi-physics phenomena, right? And immersed methods are very well suited for these problems, but high-fidelity 3D results at kind of the Reynolds numbers that we need, not 10 to the 6, 10 to the 7, but for many problems, 10 to the 3, 10 to the 4, right, in that range, are rare. And so our numerical strategy combines high-order discretization, adaptive grids, and large-scale parallelization, moving towards high fidelity and high throughput multi-physics 3D simulations. And I hope to have shown a couple of applications of how we can use our solvers to generate high fidelity simulations results and use them for the modeling, design, optimization, and control within complex flow environments. So with that, I'm wrapping up. Credit to my group. These are all my grad students, Lingbo and James, my first students who are graduating this year, fingers crossed. Shinjay has been starting 2 years ago, and then Preston, Nicholas, and Nigel are the newest members. Preston graduated with his master's last year. And these are my postdocs. David and Thomas have moved on. Hamid and Mahmoud are right here. A couple of undergrad students that helped out with the morphing wings, and our collaborators across the US and Europe. And of course, my funding from the Army, DOE Army MathWorks Sea Grant, and compute resources from Access, formerly Exceed, and DOE NERSC. So, and thank you for listening and staying here.
Okay. Questions? Themis.
Okay. Thank you for the nice presentation, Will. So I'm trying to understand a bit better the connection or the potential connection between the optimization problem, where you use a surrogate model, right?
Yeah.
And the higher order methods down the way, right, that you do.
Yeah.
So, like, to me, there is a logical gap there. Like, you are trying to solve something with really high fidelity, but eventually you have, like, if you want to do something useful with it, you have to do optimization through, a surrogate model.
Yeah.
In that sense, is it, like, really helpful? Yeah, they are orthogonal. Is it really helpful? Because you miss all the information, right? If you use the surrogate model, you're trying probably for something more rough.
No, you're totally right. And I agree. I think the piece that's missing that I didn't get to here is the grid adaptation technique that we use. So the way that we do mesh adaptation with our wavelet approach, one of the benefits of using that approach is that we get a somewhat formal relation between the error we make in the simulation and the thresholds we use for the grid adaptation. And that kind of formal relation is often absent with existing grid adaptation techniques, where it's more ad hoc. You choose a thing and you get an error. And so when I talk about high throughput, I mean dialing that threshold to a very coarse value. So we can get very high throughput simulations with the 3D, with the multiphysics, with all these complex physical phenomena, but at resolution levels where we essentially throw away a lot of the unnecessary information to get low fidelity results. And that, reducing the order of accuracy maybe part of that, right? It's about now generating low fidelity, high fidelity, or adaptive fidelity. But I think the multi-resolution grid adaptation that we developed with the wavelet transforms is going to be key in spanning a very large spectrum on the fidelity region, all the way from very high, but also in a controllable manner, all the way to low, high throughput simulations, low fidelity, high throughput.
And a follow-up question, if I may. For the circuit modeling, can you elaborate a little bit about what is the dimensionality of the parameter space you're optimizing? What is the the techniques you are using to do circuit modeling, or what optimization?
So the dimension of the parameter space in the final problem is order 10, 9 or 10. So we have four hinge angles, 4 hinge stiffnesses, and then an incident angle. So I guess 9. The optimization algorithm is a genetic algorithm off the shelf. And then the surrogate model is a deep learning architecture. It's nothing, yeah. So thinking about your work, I think moving into active learning and that's going to be a very cool addition to it.
Okay, sounds good. Thank you.
All right.
Some more questions. Can I ask a question on the flexible phase?
Yeah.
In the simulations you've done, it was actuated in specific points, correct?
Well, so we changed the curvature, and changing the curvature means you need to have some sort of boundary condition on the tangent vector to the trailing edge. So you can change the curvature, keeping the leading and trailing edge constant, and just change it, or you can change the curvature starting at the leading edge, and then your trailing edge is going to do something different. And so we looked at both of these scenarios as ways of curvature. And the results I showed were for the case where we keep the kinematics of the chord line essentially identical and just change the camber as it flaps. But the other case where you're, which is maybe more what fish do, which is shearing the rays at the leading edge and then changing the curvature like that, it's going to affect essentially 2 things at once, the curvature and the trailing edge kinematics. And it turns out that the trailing edge kinematics are dominant in the hydrodynamic effects, more so than the curvature. So that's maybe the less interesting case.
How difficult will be to take this flexible airfoil that you have and make it into a 2-dimensional fish with free motion?
So you can account for
all the...
I think it's doable. I think especially in 2D. 3D is going to be a bit harder, but also doable. We did all that in my PhD. I think an interesting kind of question related to that might be the use of curvature to steer, essentially to maneuver as well. So can you fine-grain your motion so that maybe the flapping harmonics govern your large-scale motions, but you can make very fast adjustments by changing curvature on the fly without changing the global. And there's maybe more biomechanics question whether the muscle groups governing the large and the small scale behavior, but I can imagine curvature control acts as like a fine-tuner maybe on top of the large scale motion.
And one last question from me.
You showed some results on efficiency and thrust. What kind of efficiencies did you achieve in absolute numbers of propulsive efficiencies? Do you remember? I don't remember the actual. I'll send it to you. I can put a number. It's I think between 20 and 30%. Yeah. Question in the back.
Yep. I can yell if that.
Yeah, it will help with the YouTube listeners afterwards.
Hi, Wim. Thanks for presenting.
Sure.
My quick question, I think I missed it in your presentation with the morphing bodies. Was the camber change in those foil shapes, was that due to the resonant FSI interaction of the foil, or was that an active control of the camber in the thrust cycle? So
those were pure fluids and imposed deformations. So we didn't solve for the structural mechanics in that case. Okay. So my reasoning was, and still is, that in a lot of the FSI scenarios, the only thing that matters for the flow is the shape of the body over time, right? That determines uniquely the fluid dynamics. So, and you can achieve that shape change using different structural designs, different structural mechanisms. So I was interested in what if I just fix that shape and parameterize it and use it to find A, the optimum, and then B, maybe design later structural designs that can closely fit that unique shape or that optimal shape through the combined FSI effects.
Thank you.
Yeah.
I want to ask about the first part, the vortices.
Yeah.
So, all this knowledge that we learn, I mean, beyond the intellectual value of understanding what these two vortices do, like the vortex tube, right? How can we use it on the practical level? Like, what did we learn that eventually, will make it useful to implement? Because I think that was the motivation, right, when you started, that you want to use it for design. So, how can that go there?
Yeah. I think it needs a few more steps. I think we just kind of covered the core fluid mechanics phenomena. Using it, we didn't get to that in this study. I think the next step is one of these two things that I mentioned at the end, is either link it directly to a boundary layer perturbation, like what type of boundary layer off of maybe an oscillating wing would generate twist wave distributions in the vortex. The other part would be, can we control or perturb the vortex in a way that ultimately induces this bursting and dissipates energy as fast as we can? So can we solve an inverse problem related to that? So I think now that we better understand what's the physical mechanisms that are going on, we can start to think about those follow-up questions.
So I know you don't have the numbers with you right now, but I was just wondering, like efficiency-wise and thrust-wise, after all this optimization, are we, the state of the art, is it like more efficient than natural fish, or are we, what are we compared to them?
That's a great question. I think there's different types of efficiency that you can develop. I think when you go to the more practical side of things, so with the simulations, I get one efficiency, which is the thrust coefficient over the power coefficient, essentially, right? And that's 2D, relatively low Reynolds number. And so what I'm comparing more is the difference in efficiency from a rigid fin, like what type of improvements could we get relative to the efficiency. So your question is on the absolute value of the efficiency, and then I think the more relevant question is what type of efficiencies do we get in practical systems. There, the efficiency is combining the hydrodynamic efficiency with the structure and the actuation and all these other effects. And that's very far from, I think, where fish are at the moment. So I think there's work to be done, maybe on the hydrodynamics, but also on all these other components of the actual robotic fish. I think the flapping fin the fish is an inspiration. But there's even thinking about appendages and rudders and other kind of morphing foils that are not attached to another bio-inspired robotic fish are still relevant in practice. Looking at appendages of or hydrofoils or rudders and using active deformation as a potential alternative design. So I think that's kind of the other part of the inspiration that we're working from.
Thank you very much.
All right.
Question, since I have the opportunity. It looks like with your methodology, with the immersed boundaries, you can arbitrarily change the body, correct?
Yeah.
So one of the major morphing issues is when the body changes even volume and area.
Yeah.
So for example, when the bats fly, they have a huge change of the span of the wing. Mm-hmm. And this is dynamic. It's every cycle it goes up and down.
Yeah.
Can you say a little bit more about it? Because that could be an intriguing problem to study.
From the numerical side or the physics?
for both?
Yeah, I think right now all our numerics are volume preserving. But where we're going is not necessarily a limitation that is hard on the methodology. So it's something that is definitely possible in the numerical side. In the physics, I think so. When we talk about multi-physics, I'm thinking ultimately about problems where there's separate domains, maybe flow and structure or air and water, and those domains have an interface that couples their behavior through some boundary conditions like stress continuity and displacement. And so intrinsically, we need to be able to handle volume changes in that setup. So everything we do is designed to be able to allow that ultimately. So nothing in the numerics is and specific on the application. I haven't spent a lot of time thinking about volume changing as a locomotion or another or a shape morphing effect. It's intriguing. I'd like to talk more.
Yeah, one other problem that is related, is bubble dynamics.
Yeah.
When they can change from being bubbles to being nothing, to merging into the fluid. You have complete phase change.
Yeah.
What happens to the vorticity? What happens to the momentum?
Yeah.
Those are very fundamental questions.
Yeah, and I think that's where you at some point switch to subgrid scale modeling in a lot of the methodologies that are maybe, and maybe you're asking about simulating that way farther down. I think it's another problem that is all these features. It's multi-physics, it's 3D, I guess, unless you're fully ideal axisymmetric. And it's large changes in scale over space and time, so adaptive grid refinement are useful. I think those are kind of type of fundamental scientific problems that we can almost only handle with immersed methods that are ultimately high order accurate and rely on some adaptive grid refinement and perhaps also need the supercomputing capability. So it's definitely among the class of problems that we are motivated by.
Okay, any other questions? If not, I would like to thank our speaker for a wonderful talk.
Thank you, everyone. Thank you.